So up until now, we've been making the assumption that the reactions we've been using have been at equilibrium. But how can we tell if a reaction is at equilibrium if we're unsure? And more importantly, if a reaction is not at equilibrium, what direction must the reaction go to obtain equilibrium? So we're going to determine this by finding what's called a reaction quotient, Q, and this number will tell us what direction a reaction must go to get to equilibrium. Before we get started with this, I want you to understand that if I have a zero concentration of a species involved in an equilibrium, the reaction must go in the direction to make that species. So I cannot have a zero concentration of any of the species involved in an equilibrium. And this is because the equilibrium expression must be equal to some value Q, and if I plug a zero value into my equilibrium expression, that is not going to be true. It's not going to be equal to the equilibrium constant. So here, if I add into an O2, initially I have a zero concentration of NO. This means the reaction must go to the right to make some of the NO. So some of the nitrogen and some of the oxygen are going to be used up to make NO. So I know the reaction's going to the right. I didn't need to find my reaction quotient. So the same thing is true if I just put NO into a reaction vessel. That means initially I have a zero concentration of N2 and O2. I can't have that, so I already know the reaction must go to the left. As it goes to the left, it uses up N2, NO, and it makes N2 and O2. So I know the reaction is going to go to the left. I don't need to find my reaction quotient. So if I have non-zero values for the concentration of the species involved in my equilibrium, I then must find the reaction quotient Q to tell what direction the reaction needs to go to get to equilibrium. So we do this by finding the equilibrium expression for the reaction and then plugging in the values given. The number we get out is going to be Q, which means that we are possibly not at equilibrium concentrations. Then what we do is we compare Q to K, and this relationship tells us what direction the reaction must go to reach equilibrium. So if Q is less than K, the reaction must go to the right to reach equilibrium. If Q is greater than K, the reaction must go to the left to reach equilibrium. And if Q is equal to K, the system is already at equilibrium. So if I give you the following reaction and tell you that it's involved in an equilibrium, and I give you the equilibrium constant, and I also give you some initial concentrations of the species involved in the reaction, I then want to find out what direction the reaction must go to reach equilibrium if it is not already at equilibrium. So what I do is I go ahead and find the equilibrium expression from the reaction. So remember, that's products divided by reactants raised to their stoichiometric coefficient. And then what I do is I plug the initial values into my equilibrium expression. So here, because we're using non-equilibrium values or possibly non-equilibrium values, the number we're going to get out is Q. So I plug the numbers given into my equilibrium expression and I get a value out. And in this case, the value is 0.010. I then compare Q to K, and in this case, Q is less than K. That means the reaction must go to the right to reach equilibrium. So if you think about it, this makes sense. What we want is to reach equilibrium, and when we're at equilibrium, Q is equal to K. In order to get Q equal to K, that means that the concentration of CH3OH must increase and the concentration of CO and H2 must decrease. And we do that by pushing the reaction to the right. So as the reaction goes to the right, the Q value will increase until finally Q is equal to K. Then we have reached equilibrium and the reaction will stop moving forward.